Hello, ladies and gentlemen. Welcome back to Chapter 6, Probability. I'm going to go through a whole bunch of examples. Please, the more examples you can see and the more problems you can practice, the better you're going to get at probability. Again, on that AP test, I've been looking at old AP tests. They love probability questions. They love probability questions. And sometimes some probability questions seem really straightforward, but then there's little tricks in there that you need to be aware of. Before I continue, though, I do want to point out that the problems that I'm going to go through right here, right above the video, I'm going to do a 2003 AP question number 2. Okay, that's what I'm going to end with. And then all of these other examples that I'm doing right now are right here in a PDF if you want to print them. Okay, some of them are multiple choice, some of them are free response. And then down here underneath, I highly recommend watching this conditional probability with Bayes' theorem. It's on Khan Academy. Click on that and go watch that video, please. All right, I know there's a lot of stuff in this chapter. This is a very, very important chapter. If I had to rank this chapter as like from most important to least important, for the AP test, I would say that this is probably the most important chapter because everything else behind this with probability falls into place. All right, here we go. So let's go ahead and start looking at problems here. All right, so in this first problem, we've got a multiple choice question. It says, given two events A and B, if the probability of A is 0.43, the probability of B is 0.26, and then it says the probability of A or B is 0.68, the two events are. Okay, so this is where you need to know what all of these things are. Is it A, mutually exclusive but not independent? Independent but not mutually exclusive and independent, neither mutually exclusive nor independent. E, not enough information is given to determine whether A and B are mutually exclusive or independent. Okay, well, ladies and gentlemen, I will tell you it's not E, because they do give you enough information here. So what in the world do we need to do to solve this? Well, let's find out. So the first thing I'm going to check out, ladies and gentlemen, is what it's saying up there. Okay, it's saying that the probability of A or B is 0.68. But if I take the probability of A, ladies and gentlemen, okay, if I take the probability of A and the probability of B, and I actually add those together, okay, 0.43 and, plus 0.26, ladies and gentlemen, I get 0.69. What? It says, though, that the probability of A or B is 0.68. Okay, well, that means that they must be sharing something. So what I'm going to do is I'm going to draw a Venn diagram here. Okay, and I'm going to put A here and B here. Well, if they're saying it's 0.68, well, what's the difference? The difference is 0.1, right? So that must mean right here in the center, it's 0.1. And then this is 0.42, and then this is 0.25. Okay, yeah. So it's both of them added together have to add up to 0.68. So, but when I looked at them up here, they added up to 0.69. So guess what, ladies and gentlemen? They share something. So that means they're not mutually exclusive, right? So the mutually exclusive parts are out. So that one's out. Okay. Independent. Well, no. They share something. So they've got, they're not independent. Okay. They're dependent, right? Okay. So that part doesn't match. Mutually, oh, nope, not mutually exclusive. And we already ruled out E, so guess what, folks? This one is neither mutually exclusive nor independent, which means it's dependent. Okay? So a little trick there. Okay? Whenever you're given some probabilities, you're going to want to verify what they're saying. Okay? So you might have to draw some pictures and do something. It doesn't look like you should have to do anything mathematically, but I had to figure out, well, they say 0.68, but when I add them, it's 0.69. What does that mean? Oh, yeah, they overlap. Okay? All right, let's keep going. Next one. All right, if two events A and B are mutually exclusive, then the probability that both A and B occur simultaneously is. Okay, this one's pretty easy, folks. Mutually exclusive means they don't share anything, okay, right? That's what we just talked about. Mutually exclusive. So, they can occur simultaneously? They can't. Mutually exclusive events cannot occur simultaneously. The probability is 0. Okay, you got to know your rules. You got to know what mutually exclusive means. You got to know what independent means. You got to know what dependent means. All right? All right, moving on. Next one. The probability that Ted enrolls in an English class is 1/3. If he does enroll in an English class, the probability that he enrolls in a mathematics class is 1/5. If he does not enroll in an English class, the probability that he enrolls in a mathematics class is 3/5. If we learn that Ted enrolled in mathematics, what is the probability that he enrolled in an English class? Hint, tree diagram, and conditional. Okay, well, let me draw my little stick person here for Ted. All right, so here's Ted. Now, Ted might take the English class, and again, the probability of that is 1/3, right? Okay. That means not an English class is 2/3. Well, what else do we learn? Well, we learn that if he does take an English class, then to take the math class, the probability is 1/5, right? Yep. And if he doesn't take the English class, then taking a math class, the probability is 3/5. Oh, okay. All right, so I've got my tree diagram there. I've got it laid out. Okay, so now let's see. The conditional probability is that the probability that he takes an English class given a math class. Okay. Let me go back and read it again. Ted enrolled in a math class. What is the probability that he enrolled in an English class? Okay, this is a conditional probability. It's telling you he enrolled in a math, and they want to know, well, what's the chance he enrolled in an English class? So that's the conditional probability. Let me pull this back in. Remember, conditional probability is this, folks. Okay, the probability of B given A is the probability of A and B divided by the probability of A. All right, so with what I have here, ladies and gentlemen, that means I'm going to take the probability of English, I'm going to use E, I'm not going to write out the whole thing, and math, divided by the probability of math. Ah, okay. Well, let's see. English and math. Well, that probability, if I multiply these together, folks, 1/3 times 1/5, okay, because English and math, that's 1 out of 15. Okay, here, ladies and gentlemen, if I do no English and math, that would be 6 out of 15, right? Okay, well, let's see here. So English and math is 1/5, 1/15, sorry, divided by the probability of math. Well, folks, the probability that he's going to take a math class is these two added together, because he's going to take a math here, or he's going to take, or, notice I use the word or he's going to take a math that way. And that is 7/15. Interesting. Wow. All right. Well, I'm going to divide by 7/15, folks. Okay, well, isn't that the same as 1/7? Because the 15s ends up canceling each other. All right, so let's see what decimal that gives us. So 1 divided by 7, ladies and gentlemen, is going to be 0.1428. You bet. So that answer, ladies and gentlemen, is B. Okay, let me re-emphasize things here. So I set up a tree diagram, English, and then the probability of taking math. No English, then the probability of taking math. So English and math turns out to be 1 out of 15. No English and math turns out to be 6 out of 15. So the probability of taking a math class is 6/15 or 1/5, which is 7/15. It's a conditional probability, English given math, which is English and math divided by the probability of math. 1 out of 15 divided by 7 out of 15 is 1/7, which is 0.143. Okay. Next. A medicine is known to produce side effects in 1 of 5 patients taking it. Suppose a doctor prescribes the medicine to 4 unrelated patients. What is the probability that none of the patients will develop side effects? Okay, ladies and gentlemen, well, the probability 1 in 5 will develop side effects. Okay, the medicine is known to produce side effects in 1 of 4. Okay, but the question is, what is the probability that none of the patients will develop side effects? So that means 4 out of 5, right? Okay, so the probability that none of them will is going to equal 4/5. So the first patient does not develop it, and the second patient does not develop it, and the third patient does not develop it, and the fourth patient does not develop a side effect. So 4/5, you could go 4/5 times the probability of the second patient, and the third patient, and the fourth patient, or you could simply go 4/5 to the 4th power. And if you type that in on your calculator, ladies and gentlemen, so 4/5 to the 4th power, as I said, this is probability you're going to have to practice and see a bunch of different examples. That's why I'm doing these examples. So the probability is 0.4069. Okay, that's using rule number 5. Okay, that's using rule number 5. This last one, that was using rule number 5 and rule number 3 with the conditional probability bit. All right, moving on. An automobile service station performs oil changes and tire replacement as well as other services. 60%, let's see, what color do I want to use here? 60% of its customers request an oil change. 30% request tire replacements and 10% request both. Oh, a customer requests an oil change. What is the probability? So they request an oil change. What is the probability this customer does not request a tire replacement? Hint. Now, they're not going to give you these hints on the AP test, folks. They're not going to give you these. This is why we've got to look at these and really think and practice and review, go back and review and think. All right, so a Venn diagram would be useful, and it's conditional. All right, so let me get my Venn diagram. So I've got 2 things going on here. I've got an oil change and I've got a tire rotation. Now, 10% request both. Again, I'm going to change that to a decimal, so 10% request both. 30% require tire replacement. So what's left over? Remember, we got to subtract 10% from 30%, so 20. And then it says 60% want an oil change. Well, take 10% from that, so what's left in there? 50. Okay, think about it. We've got to take that 10% away from those. All right, now if I add those together, ladies and gentlemen, that only adds up to 80. That means there's 20 left over for the outside. Okay, well, let's think about this. I got to write this out. So the question is, what's the probability of not a tire rotation given an oil change? All right. Well, remember what this means, folks. This means the probability of not tire and oil divided by the probability of oil. All right, well, not tire, so not a tire and oil. So that would be this, folks. Not tire and oil would be this. So that would be 0.50 divided by the probability of oil, which is 0.60. Wow. Okay, that was it. So we're going to take 0.5 and divide it by 0.6, and we're going to end up with 0.8333. Oh, I love this stuff. This is great. This makes you think. This makes you think. So draw something out. You got the option of, okay, would a Venn diagram work here? Tree diagram work here? Okay. Practice, practice, practice. Okay, let's keep going. I got a bunch more. All right, in this one, an experiment has 3 mutually exclusive events. Oh, they're mutually exclusive, it says. A, B, and C. The probability of A is 0.12, the probability of B is 0.61, and the probability of C is 0.27. Which of the following must be true? Okay, well, first of all, mutually exclusive, ladies and gentlemen, if they're mutually exclusive, they're not independent. So that's out. Mutually exclusive events, again, I've said this, I don't know, in the videos, this may be my 5th or 6th time. Mutually exclusive events are not independent. All right? So, how about number 2? It says the probability of A and B are 0. Well, yeah, mutually exclusive events do not overlap. So that's true. That's true. The probability of B or C is the probability of B plus the probability. Well, yeah, that's true. You can add mutually exclusive events together. So in this situation, folks, it's got to be D. It's the 2 and 3 only. All right, let's keep going. Next. All right. People with type O negative blood are universal donors. That is, any patient can receive a transfusion of O negative blood. Only 7.2% of the American population has O negative blood. If 10 people appear at random to give blood, what is the probability that, at least one of them is a universal donor? Folks, as soon as I see those words, I think of rule number 4, the complement rule. Okay, so the question is the probability of at least one is universal. Now remember, at least one means one or more. Well, sorry it's so sloppy. At least one means one or more. Well, folks, you might have one. You might have two. You might have three. You might have four. You might have five. You might have six. You might have seven. Whoa, 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 whoa. I can't figure that out. So I have to use the complement. Now, what in the world would be the complement of that? Well, 1 minus the probability of no one, none are universal. So that I can figure out. Well, folks, up here it says 7.2% of them are O negative. Well, I need none of them to be O negative. So I've got to go ahead and take my 100% minus my 7.2%. And I'm going to get, let's see, 92.8%. Now remember, I cannot use the percent. I got to change it to a decimal. Okay, so think about it. I'm doing the opposite. So here we go. So I'm going to go 1 minus 0.928. And folks, there are 10 people. So that will be to the 10th power. None of them. So if I take 1 minus, none of them having type O blood, I am going to get the answer. All right, so here we go. So 1 minus 0.928 to the 10th power. Voila. Okay, so 0.526. So A is our answer, ladies and gentlemen. Isn't that cool? Rule number 4. And then you got to think, okay, I have to, oh, the ones that don't have type O blood, that would be 92.8%, and 1 minus. Okay, lots of things to think about. I like that problem. I really do. I like that one. All right, moving on. All right, next one. If A or B is the sample space. So A, that means A, whatever event A is and event B is, that's everything because it's the sample space. And the probability of A and B complement is 0.25. And the probability of C complement, or A complement, sorry, is 0.35. Then what in the world is B? Ooh, this sounds like a Venn diagram situation to me, folks. So let's see here. So let's see, A or B is the sample space. Okay, well, I'm going to make my Venn diagram like this. Let's see, this is A and this is B. All right. So let's see here. I got to think through this. It says A and B complement is 0.25. Oh, not B. Okay, that tells me that this part of the circle is 0.25. Think about it. And there's nothing on the outside of the circles. So I know what's outside because right here it says A and B is the whole thing. So there's nothing that's outside those two circles. So I can put a 0 there. Okay, so now let's see. A and not B is 0.25, and A complement is 0.35. Oh, A complement, so that has to be what B is. So that's 0.35. Well, okay. So now when I add this all together, including the center, okay, if I take 0.25 and 0.35 and whatever's in the center, it's supposed to add up to 1. Oh, I got this. All right, so I'm going to go ahead and take 0.25 away from 1 and 0.35 away from 1. And let's see, what do we get? Let's see, those add up to 60. So it looks like this is going to be 0.40. So, ladies and gentlemen, what's the probability of B altogether? B altogether. Now, this is B only. This was the B only, the 0.35. So B altogether, folks, add those two together, and it looks like we get 0.75. That's a pretty cool problem. I like that. All right, let's keep going. Suppose that for a group of customers, the probability of eating pretzels is 0.75. All right, well, let's see here. So eating pretzels is 0.75, and the probability of drinking a Diet Coke is 0.65. Okay, so the probability of pretzels is 0.75. The probability of drinking a Coke is 0.65. Further, suppose that the probability of eating pretzels and drinking Coke, so the probability of pretzels and Coke is 0.55. All right, determine if these two events are independent. Oh, yes, finally one of these. All right. They really like this type of question on the test. Okay, so let's see here. Well, this is the information that it gives me. So what I'm going to do next, ladies and gentlemen, is I am going to actually take the probability of pretzels times the probability of Coke, and I'm going to see what I get. So that would be 0.75 times 0.65. And, well, what I get when I multiply them is 0.4878. Okay, well, let's think about this, folks. They said that the probability, they say right here, the probability of drinking, whoops, wrong one. Sorry about that. Let me erase that. Right here, eating pretzels and drinking Diet Coke is 0.55. So that's, but I just multiplied those together and I got 0.4878. Okay, so you know what's coming, right? Since the probability of pretzels and Coke does not equal the probability of pretzels times the probability of Coke, the events eating pretzels and drinking Coke are not independent. If they were equal to each other, then we could say they're independent. But since they do not equal to each other, they are not independent. Okay, think through that. Listen to it again. You're definitely going to have one of these on your test. All right, moving on. My test. Next one. All right, here is the assignment of probabilities that describe the age in years and sex of randomly selected American students. What is the conditional probability that the student is female given the student is at least 65 years old? Okay, so let's write this out. So the probability of female given at least 35 years old. So I'm just going to use greater than or equal to 35, right? Because that means 35 or older. Now, again, you should, if this was an AP question, you should be writing this out like this. Okay? What I'm writing, you should be writing. All right, so that means the probability of female and at least 35 divided by the probability of at least 35. Okay, well, let's see here. So the probability of female and at least 35, that would be this right here, 0.09. divided by at least 35. Well, folks, we're going to have to take and add those two together, and looks like we're going to get 0.13. So we're going to divide by 0.13. So let's see, 0.09 divided by 0.13. And it looks like it's about 69%. So approximately 0.69. Now, if this was my test, you need to write, and on the AP test, write a sentence conclusion. Okay, always be writing a sentence conclusion. So we would say there is about a 69% chance that if the student is at least 65, that they're female. Okay, you need to write a sentence conclusion. I'm not going to do that to save a little bit of time because I'm already past 30 minutes and I have several more to go. All right, moving on. All right, if 4 cards are drawn from a deck of 52 playing cards and not replaced, not replaced. Remember, I did talk about replacement and without replacement. Find the probability of getting at least 1 heart. There's the words at least again. I automatically think of rule number 4, the complement rule. All right, so the probability of at least 1 heart. Well, the complement of that's going to be 1 minus the probability of no heart. Okay, and then it's not without replacement. Now remember, there are 13 hearts in a deck. Right? 13 hearts in a deck. All right, so that means 52 minus 13, that means there are 39, did I do that right? 39 that are not hearts. Okay, because I have to use that, right? Because I'm doing the complement. No hearts. There's 39 cards that are no hearts. All right, so here we go. So what we're going to do is we're going to go 1 minus, okay, so the first card, there's 39 out of 52. And then you draw another card, but you don't put that first card back. So now, you got to be careful on this one. Now you have 38 cards that are not hearts, and there's 51 left. Notice I went down by 1 on both of those. Times 37 out of 50. And then the fourth one, 36 out of 49. This is why I picked this problem. All right, I love it though. Now, you can type that in, ladies and gentlemen, on your calculator. To save time, I'm not going to show it. But you get 1 minus 0.3038. If you did just that, if you just did the multiplying all of those fractions together. So our answer here, ladies and gentlemen, is 0.6962. So approximately 69% chance of that happening, that you get at least 1 heart. So you would again need to write a sentence conclusion. I might be spelling conclusion wrong, but all right, write sentence conclusion. So the probability of getting at least 1 heart is about 69%. All right, ladies and gentlemen, let's take a look at this one. So events D and E are independent, okay? So one will not influence the other. So I'm thinking, all right, independent, okay. So the probability of D is 0.6, the probability of D and E is 0.8. Find the following, which of the following is true? Okay, well, what I'm thinking here, ladies and gentlemen, so if they're telling me the probability of D is 0.6 and the probability of D and E, which means the probability of D times the probability of, E equals 0.18. Okay, I can go with that. Now let's see here. It's telling me the probability of D is 0.6. So what I'm going to do is I'm going to plug that in here. So I'm going to kind of like do a little algebra here. So I'm going to go ahead and go, okay, well 0.6 times the probability of E equals 0.18. Let's see, divide by 0.6. All right, let's see, divide by 0.6, and it looks like we get, what is that, 0.8 divided by 0.6, 0.18 divided by 0.6 is, yep, 0.3. Okay, so that means, ladies and gentlemen, that the probability of E is 0.3. Okay, so the probability of D is 0.6, the probability of E is 0.3. So let's see. Nope, A is out. B is out. Probability of D or E? No, or means to add. So if I add those together, that's 0.9. Yeah, no, that's out. That's out. There it is. That's what it was. Okay, not too bad. You just had to think through. Got to remember your rules. So this was rule number 5, and then they threw in rule number 3. Okay, all right. All right, one more on this slide, and then I've got that problem from AP to go over really quick. All right, here we go. In women's tennis, a player must win 2 out of 3 sets to win a match. If a player wins the first 2 sets, she wins the match, and the third set is not played. Player V and player M will complete the match. I mean, compete in a match, not complete a match. Sorry about that. First part, A, let V represent the event that player V wins a set, and let M represent the event that player M wins a set. List all possible sequence of events V and M by set played that will result in player V winning the match. Okay, so player V wins. So here they are. So it might go that the player V might win the first 2 right away. Boom, you're done. Or player V might win, and then player M wins, and then player V wins. There's only one other situation here. Player M wins the first one, and then player V wins the last 2. Okay, there's player V wins. Okay, now part 2 lists the possible events where M wins. Okay, well, that's easy. So player M wins. Okay, well, that would be MM, MVM, or VMM. Okay, there we go. So what's next? So let's see. Player V and player M have competed against each other many times. Historical data show that each player is equally likely to win the first set. If the player V wins the first set, the probability that she will win the second set is 0.6. So if player V wins the first set, the probability that she wins the second set is 0.6. If player V loses the first set, the probability that she will lose the second set is 0.7. If player V wins exactly one of the 2 sets, the probability that she will win the third set is 0.45. Okay, so what is the probability that player V will win a match against player M? Okay, well, ladies and gentlemen, so the outcomes for player V to win. All right, well, there's VV, There's the VMV, and there's the MVV, right? Okay, so the probabilities, according to what it's saying here, ladies and gentlemen, so for this scenario, it's saying that it's going to be, all right, so let's see. Historically, data show that each player, is equally likely to win the first match. Well, equally likely, ladies and gentlemen, is 50-50. So, player V wins the first match. And if she wins the first match, then the chance of winning the second match is 0.6. So, the probability of that happening is 0.3. Aha, okay. Think about what I just did. All right, so again, the probability of winning the first match is 0.5 because it's equally likely. Now, the probability, okay, so let's see here. So now now it's M wins. Well, that's the complement because that means V loses. Well, it only says that if she wins the first game, the probability that she wins the second game is 0.6. So that means this is going to be 1 minus 0.6 because she lost it. Times wins the, okay, player V wins exactly one of the first two. The probability that she will win the third set is 0.45. So now this is going to be 0.45. And if I multiply all of that, I get 0.09. Ooh, I like this problem. Okay. And here, well, again, she still has a 50% chance that she's going to win or lose that first match. All right. And now the next part, she wins the second match. Well, here it says the chance that she loses the second match is 0.7. So I got to go 1 minus the 0.7 because she won it. See, she won it. And then times the 0.45. Ha. And that gives me 0.0675. Okay, so what is the chance that she wins? Well, we take these three and add them together. And we get 0.4575. So the probability that player V wins a match against player M is 0.4575. Okay, rewatch that if you need to. Think about it. Again, read carefully, reread again. All right, C. What is the probability that a match between player V and player M will consist of 3 sets given that player V wins the match? Oh man, okay, so let's see. The probability that wins 3 sets, or 3 sets, given V wins. Well, that's the probability of 3 sets, not wins 3 sets, 3 sets, and V wins, given the probability that V wins. Oh, we're going to have to use the answer we got in this last problem, aren't we? Okay, well, the probability of 3 sets, ladies and gentlemen, is these two added together, right? Let me get blue here. These two added together, that's the 3 sets. Okay, and if I add those, if I take the 0.09 plus the 0.0675, that's the 3 sets. Now divide by the probability that she wins, 0.4575. And guess what? That's going to give us about 0.344. So there's about a 34% chance that player M will consist of 3, or the match between player V and player M will consist of 3 sets, given that player V wins the match. All right. Okay, there's another part to this, I think. And nope, that was it. That was it, ladies and gentlemen. All right, I thought there was a part D, but there's not. All right, now, wow, 46 minutes. Ooh, boy. All right, let's get to this problem here. All right, here's a 2003 stats pre-response question. So, get myself organized here. A simple random sample of adults living in a suburb of a large city was selected. The age and annual income of each adult in the sample were recorded. The resulting data are summarized in the table below. All right, so here's the data. What is the probability that a person chosen at random from those in the sample will be in the 31 to 45 age category? Okay, well, 31, so that would be 89 out of the 207, right? So we're going to write the so this is A. So the probability of age 31 to 45 is going to equal 89 divided by 207, which is approximately 0.42995. All right, moving on. B, what is the probability that a person chosen at random from those in this sample whose incomes are over 50,000 will be in the 31 to 45 age group? Okay, this is a condition, folks. So the probability that age 31 to 45 given income over 50,000. Okay, well, remember what that means. That means the probability of age 31 to 45 and income over 50,000 divided by the probability of income over 50,000. Okay, sorry, I kind of abbreviated that there. All right, so first of all, 35 and that. So let me move this. So 31 to 35, income over 50, that's 35 out of the condition, which is over 50,000. So 35 out of 96. And that's approximately 0.36458. All right, and the last one, we'll wrap this up. Letter C. Based on your answer in parts A and B, is the annual income, here we go again. Are they independent of age category for those in the sample? Explain. Okay, well, I'm going to type this one out instead of writing it out. All right, make that a little smaller. So, if annual income and age were independent, the probability in A and B would be equal. Since these probabilities are not equal, annual income and age category are not independent for adults in this sample. All right, remember what it means? I showed you several times about independence. It pops up a lot. Okay, rewind, watch that if you need to, because my video is plenty long. So All right, ladies and gentlemen, we'll see you in class soon.